interesting things today. We're going to learn about the mean value theorem, which says if you're really, really mean, good things are going to happen for you. Look at our president, right?
Aww.
Then we're going to learn about antiderivatives, how to do the opposite of take derivatives. And then finally, we're going to learn about increasing and decreasing functions. And we're going to use this knowledge tomorrow to determine analytically whether I have a relative max or relative max or relative min. That way you don't have to make a graph to determine if you have a relative min or max. You can just use what you know about increasing and decreasing functions. So first, let's do the mean value theorem.
God bless you.
Okay. Suppose I drive to Las Vegas. So I drive to Las Vegas. Alrighty? And let's say I travel 210, well, for me it's about 240. Let's say I travel 240 miles in 4 hours. So I must have been coming with my wife, because if it was me alone, it would take me 3 hours and 15 minutes or so. But I'm with my wife, so we have to make stops and whatnot. So it takes me 4 hours to drive 240 miles. Okay, going to Las Vegas, baby. Las Vegas, 240 miles in 4 hours. You tell me, what's my average speed for that trip?
80, 60 miles.
Good. My average speed is 60 miles per hour. That's my average, or my mean speed is 60 miles an hour, right? Total distance divided by time gets you your average speed. So here's my question to you. Guaranteed, is there one point during this trip where I must have been traveling at an instantaneous speed of 60 miles an hour?
No.
Or could I make this trip, could I average 60 miles an hour for a trip and never for one moment ever actually be going 60 miles an hour?
No.
How many people say, sure, I could go the whole trip averaging 60 miles an hour, but never at any particular instant be actually going 60? How many people say, yeah? Okay, and how many people say, nope, can't happen? Okay, good. You're right, it can't happen. The majority, I just want to tell the video viewing audience, the majority chose no. Why not? Why couldn't you never be going 60? Yes, well, I love you dearly, Andy.
Yeah,
let me get someone else. Someone else tell me. Well, why couldn't? Yeah, Kylie.
For your average to be 60, you'd have to at some point be going more than 60, and if you're going more than 60, if you're speeding up, you have to at some point hit 60. Because you can't just skip a value.
Thank you. You can't just skip a value. Yeah, if at some point I'm going faster than 60, then at some other point I had to be going less than 60. If the average is 60, I'm just saying what you said verbatim. And if I'm going to go from higher than 60 to lower than 60, then at some point I had to hit 60. Okay? But that is, if I were to make a graph of this situation, okay, this is time in hours, and this is distance in miles, okay? And I know I go 240 miles in 4 hours, right? So I start here at home and I end here 240 miles away from home in Las Vegas, alrighty? But I'm obviously not going 60 miles an hour the entire trip. You know, we start off and we're all excited to go, so we're going pretty fast. Are you guys okay that the slope of this graph, the rise over the run, is miles per hour? So the slope of this graph is telling me what my speed is. And the slope of the tangent is going to get me my instantaneous speed. So we're going pretty fast, and then we kind of slow down a little. And then we stop at Baker, the location of the world's largest thermometer. And maybe we stay there for a while so we don't make any progress at all. Then we get going again. Okay, and then we slow down because we hit traffic, and then we're in Las Vegas, okay? Well, tell me graphically, the average speed is 60 miles an hour, 240 over 4. What is that graphically? Yeah, Justin. Good, a straight line, this straight line, and tell me what specific characteristic of that straight line? Yeah, the slope. Thank you, Omar. It's the slope. I want you to see that the average speed is the slope of, and we call that the secant line. It's the slope of the line joining the initial point and the final point. Okay, the slope of the secant. my instantaneous speed had to be 60 miles an hour somewhere, okay? How do I get the instantaneous speed from a displacement versus time graph or a distance versus time graph? What's that? Yeah, the tangent line, the slope of the tangent. The mean value theorem says this. If I've got some graph and I draw a secant joining the initial point and the final point, then somewhere in between the initial and final points, there has to be at least one place. Here there's 1, 2, 3, it looks like. Okay, but there has to be at least one place where the instantaneous rate of change is equal to the average rate of change. That is, to put it in terms of my trip to Vegas, there has to be at least one point where the slope of the tangent, there has to be at least one point where your speed, your instantaneous speed, is equal to your average speed. That is, there has to be at least one point where you're actually going 60 miles an hour. Okay, so let me put it in math terms. Here it comes, the mean value theorem. Let me put it over here. Mean value theorem. If f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, I didn't mean to put a comma there, then there is at least one point C in the open interval from A to B such that f prime of C equals f of B minus f of A over B minus A. Or to express this in words, the slope of the tangent is equal to the slope of the secant. Slope of the tangent at x equals c is equal to the slope of secant joining x equals a to x equals b. Slope of the tangent at x equals c equals the slope of the secant joining, or another way to say it is the instantaneous rate of change. Instantaneous rate of change at x equals c equals the average rate of change from x equals a to x equals b. Before we start doing problems where you find this C that demonstrates the mean value theorem, I want to say more how important it is that f of x be continuous, really that f of x be differentiable. Because if it's continuous, then it's also different. I mean, if it's differentiable, it's also continuous. But we want it to be differentiable and continuous. I can draw a trip where this doesn't happen. I can draw a trip where I average 60 miles an hour, but at no time am I actually going 60 miles an hour. Could someone describe such a trip? I gotta start here and I gotta end there. 244, alrighty. I gotta start there and end there. Can you describe a graph where I start here and end there, but at no time am I actually going 60 miles an hour? And remember, the slope of your graph is going to give you your speed.
Just go 59 miles per hour.
Okay, go 59, but if I go 59 miles an hour the whole way, then I'm going to undershoot Vegas by 4 miles. So I can't go 59 miles an hour the whole way. So let's say I start off going 59 miles an hour, then what would you have me do?
Go 61 miles an hour.
Okay, abruptly change to 61, right? That is, at this point here, I abruptly change to 61. Do you see? My car has only gone 2 speeds, 59 miles an hour and 61 miles an hour, without ever going 60 miles an hour. See? So I can draw that, but what's true? What word do I use to describe that point right there?
Corner?
Yeah, it's a corner point, thank you. It's non-differentiable. That is, my little walking men get a different slope coming from this direction as coming from that direction. And we know that's not real life. I can't make my car go from 59 to 61 miles an hour without hitting 60. You know, I can't, like, I don't know, it's not like going into hyperspace or something with Star Wars where you press a button and you instantaneously are going a different speed. You know, if I'm going to go from 59 to 61, I've got to hit not just 60, I've got to hit 59.1 and 59.2 and 59.3 all the way to 61. You see? So yeah, that's why they have to make that, you know, that provision that the function has to be differentiable in order for the mean value theorem to work. Or you could just draw a situation like this, where your average rate of change is 60, but never is your instantaneous rate of change 60. So it's important that it be different. And then, of course, if you can have it be discontinuous, where, you know, if my car is going 30 miles an hour, then it magically starts going 80 miles an hour. Or no, if my car, like if I'm in Barstow and then I snap my fingers and I instantaneously end up in Baker, then of course all bets are off, right? I mean, then I only have to average 50 miles an hour, right? I'll just, here's Vegas, here's me, I'll just average 50 miles an hour till I get to Barstow. Then I'll magically snap my fingers and now I'm in Baker, and then I'll just continue going 50 miles an hour, right? And so you can say, hey, I can have a trip where my average speed is 60 miles an hour, but never do I go anything but 50. All I have to do is just snap my fingers and go from Baker to Barstow with no time passing, you know? Or Barstow to Baker, excuse me. Because essentially your graph became, you know, discontinuous right there. All right, well anyway, hey, let's do some problems with mean value theorem. Okay. Demo, mean value theorem for y equals x squared on the closed interval from 0 to 2. Okay? Demonstrate the mean value theorem. Well, here it comes. I'm going to start by putting down the mean value theorem. F prime of c equals f of b minus f of a over b minus a. Alrighty? I have an expression for y prime, right? Y prime is equal to 2x. So are you okay that f prime of c is going to be 2 times c? F of b, that's going to be f of 2 minus f of 0, because b is 2 and a is 0. 2 minus 0. So I got 2 times c equals, 4 minus 0 over 2. So I get c equal to 2, right? No, c equal to 1. Wait a minute. Just trust my algebra. I got c equal 1. What does that mean? That means that if I make this graph, here, just 1 second. If this is my graph, y equals x squared, then the average rate of change, that is the slope of the secant from 1 to 0, has a particular slope. And there's a point between from 0 to 2, and there's a point between 0 and 2 where the slope of the tangent is the same as that, and it's right there at 1. The slope of the secant from 0 to 2 has a value of 2. And the slope of the tangent at x equal 1 has a value of 2. And so it demonstrates the mean value theorem. Yes? No, you don't even have to graph it. Not necessary to graph it. I'm just graphing it because I'm a teacher and I want to demonstrate what it means graphically.
Mr. Dana,
Yes?
isn't it just like a double-sided limit?
How do you mean?
Because like, we have like the same distance from equal, or from C on either side, and we divide by 2.
Cool. That happened just because it so happened that C was halfway between the bounds, but that won't always happen. But still, your hope in doing a double-sided limit is that you get lucky and that the slope of the tangent does happen to equal the slope of the line joining the points equidistant from that point. Does that make sense? Yeah, good. Okay, well then, hey, here you guys, I must have you guys do one on your own. Let me see if I have one for you. No, I don't. Here we go. Y equals x to the third plus, oh wait, x to the third, yeah, plus 4x. Okay, y equals x to the third plus 4x. Demonstrate the mean value theorem on the closed interval from -1 to 1. I just made this problem up, so I hope it works out okay. Good luck, you guys. And all you're doing is setting the slope of the tangent equal to the slope of the secant. I hope this works out. I got, whoop. I got plus or minus radical 1/3. Anyone get that? Okay, cool. Are you guys okay with the process? Just mindlessly plug in. And I can give you a graph. I don't know if I feel like it, but, oh, I guess I do. 0, 0. What's 1? 1, 5. What's -1? -1, -5. What is this, symmetrical? I thought it was going to do some crazy thing. I don't know. I think it does this sort of thing, but I'm not sure. But anyway, if I connect these 2 points, I've got a couple of points where the slope of the tangent is the same. Yeah. I don't know. I don't know what it looks like. I'm done. I'm done with mean value theorem. Any question or problem on this? So you're going to get a chance. Yeah, Zach.
It's like a follow-up to my second question. So if the second derivative is a constant, then will it always be in the middle?
Yes. Yeah. Smart kid. Yeah, smart kid. My goodness. Yeah, how did you know that?
I don't know. I just,
Yeah, it ends up being that way. If it's a parabola-ish thing, then it's always gonna be in the middle. At least that's my understanding. I'm gonna have to actually think about it, but my first reaction was to say, yeah, you know? If the second derivative is constant, if the rate of change of the tangent is a constant, then definitely it's like asking, you know, it's like the constant acceleration issues of physics, where because the acceleration is constant, you can say your average velocity is always halfway between your initial and final velocities. Well, that's the same sort of thing here. So, and you're going your average velocity at exactly halfway point, you know, because it's constant acceleration. So really smart kid. Okay, antiderivatives. Antiderivatives. Someone in here who is a Christian or goes to church, what is the name of that being who's going to come in the end times and be really, really bad?
Antichrist.
Antichrist. And the Antichrist, he's really evil, right?
Yeah.
And compared to Jesus Christ, who is really, really good.
He comes as good, but he turns out to be.
Exactly. Comes as good and turns out to be evil. Well, I'd like you to think of antiderivatives the same way. Okay, they come out to be good, but they're actually really, really evil. So let's go ahead and learn them. Okay?
That's a wonderful statement.
Let's say I said f of x is equal to 5, okay? And I've got some function, big F of x, and what's special about big F of x is big F of x prime ends up equaling little f of x. So when I give you little f of x and I ask for big F of x, I'm asking you for a function whose derivative is f of x. That is, I'm asking for the antiderivative of f of x. So you tell me, what's the antiderivative of 5?
5x.
How many people think in 5x? Hey, beautiful, 5x. That's great. Is that the only answer?
No.
What other answer could be true besides 5x? Yeah, 5x plus 2, right? What's another answer that could be true besides 5x plus 2?
2.5 times x squared.
No, 2.5 times x squared isn't going to get me there. Because if big F of x equals 2.5x squared, then little f of x is going to get me 5x, and that's not the same as 5.
Oh.
So that's not going to get it done. But there's another one besides 5x plus 2. What else? So yeah, 5x minus 2, or 5x plus 100, or 5x plus any constant, correct? Do you see that there's a family of functions whose derivative is 5, and that family is going to be 5x plus a constant? And so we would generally write this like this. Big F of x is 5x plus c, where c has a name, which will mean nothing to you right now, but it'll mean something later. It's called the constant of integration. But you don't know what integration is, so having the constant of integration doesn't really mean anything. But I'm hoping that you guys are able to think backwards. So let's go ahead, let's do another one. How about if little f of x was equal to 5x? Could you get me an expression for big F of x? Omar says, let's just do with what Andrew said. How many people say that they want to go with what Andrew said? Yeah, because I think Andrew was actually thinking ahead. Yeah. 2.5x squared, but is it just 2.5x squared?
2.5 plus.
Yeah, plus c, 2.5x squared plus c. Okay, hey, that worked out really well. I'd like everyone to give me this. What if f of x was equal to 5x squared? I'd like everyone right now to get me big F of x. What's big F of x equal to? Okay, time's up. What'd you guys get?
5/3.
5/3.
Good. You guys got 5/3 x to the third and then plus c. And so now it's time for us to generalize, to do the power rule for antiderivatives. What if I told you f of x was equal to x to the n power? What would the antiderivative of that be?
Plus n?
Okay, great. How many people were thinking that? Oh,
Kinda.
nobody. Okay, almost nobody. Well, I gotta tell you, that's it. You increase the exponent by 1 and divide by the new exponent. That's what it is. Increase the exponent by 1 and divide by the new exponent. That's how you can get the antiderivative of any, what do you call, anything with an x raised to a power. And then, of course, plus c. All right? So it's time for you guys to do the king of the problems. Here, I'll just put it right here. Here, what if f of x was equal to 1 over 3 times the cube root of x to the 4th? Could you get me the antiderivative of that? 1 over 3 times the cube root of x to the 4th. Good luck. I'll even get you started. What do you get for x? Okay, you knew it. By the way, by now you should have written that as 1/3 times x to the negative 4/3 power, and then you can get the antiderivative of that. Increase the exponent by 1, divide by the new exponent. Does anyone need more time? You guys are done? Okay, hey, well, let's go for it. Increase the exponent by 1, so it becomes x to the negative 1/3. How many people had their x being to the negative 1/3 power? Okay, yay for you guys. And now I've still got this 1/3 out here, and I have to divide by the new exponent. Alrighty? So this ends up just being negative x to the negative 1/3, or if you wanted to write it like an AP exam would have it, then they would probably have it like this. How many people got that answer? Okay, good for you guys, and then plus c, plus the constant of integration. Okay, hey, that's antiderivatives, and of course you can go antiderivatives with everything else, right? I mean, you tell me, what's the antiderivative if little f of x was equal to the sine of x? What would the antiderivative of the sine of x be?
Negative cosine.
Yeah, good for you. Negative cosine, because the derivative of the negative cosine gets you the sine. And one thing you're going to hear me say over and over again, whenever you get an antiderivative, always check it by taking the derivative of your answer. Is the derivative of the negative cosine of x equal to the sine of x? If it is, you got it right. If it's not, then try again. You know, always get the derivative of your answer to check that it was the correct antiderivative. Okay, then let's go ahead and deal with displacement velocity or position velocity and acceleration. Position velocity and acceleration. I want to remind you that there's a relationship between velocity and the position graph. It turns out that velocity is the derivative of position, and it turns out that acceleration is the derivative of velocity, right? Well, do you see then that the opposite would be true going in the other direction? That is, the antiderivative of acceleration gets you velocity, and the antiderivative of velocity is going to get you the position. You guys okay with that? That it'll work both ways? If the derivative of velocity gets you acceleration, then the antiderivative of acceleration is going to get you velocity? Hope so, because let me give you a problem to do. Suppose I have a formula for the velocity of a thing, and that formula is velocity equals a negative 16t plus 25, okay? And suppose I told you that at time equals 0, the position is at 50. Find S of t, find an equation for your position. Okay. Well, here's the way I'm going to do it. I need to get an expression, I need to get an expression for my position S of t. And that expression is going to be the antiderivative of v of t. Are you okay that the antiderivative of v of t is going to be negative 8t squared plus 25t plus c, the constant of integration? So that's it. I've got an expression for S of t. But how am I going to find my constant of integration, c? Yes?
It's the position at time 0.
Thank you. I'm going to use this fact, the position at time 0. And we're going to learn later on that there's a name for this. It's called an initial condition. But we don't have to worry about that right now. So yeah, at time equal t, time equals 0, S of 0 equals 50, which is going to equal negative 8 times 0 squared plus 25 times 0 plus c. And so I end up with 50 equaling c. So now I have an expression for my position. It's negative 8t squared plus 25t plus 50. Any questions or issues on this process? Yes, Andrew?
Will it always just, the c will always just equal the initial condition, or?
No, because sometimes this equation, and first of all, that's usually only going to happen if your time is 0.
Oh.
Then that happens. But even then, my S of t could involve exponentials or trigonometric functions such that plugging in 0 gets you something that isn't 0.
Oh.
Then that wouldn't happen.
Oh.
So yeah, so the short answer is no. Okay, kids, let's see if you guys can do this one. Ugh. Let me see here. Here's my expression for acceleration. Acceleration is a constant negative 10. But I told you at time equal to 0, velocity is equal to, let's say, 25. And at t equal, well, let's mix it up, t equal 2, S of 2 ends up equaling 100. Okay? Find an expression for S of t. Let me see if you guys can pull this off. Give me an expression for the position. And someone tell me in words, what process am I going to have to go through?
Two antiderivatives.
Okay, Andrew says do 2 antiderivatives. So when you do the first antiderivative, what are you finding?
The slope of velocity.
Good, velocity. And then what are you going to have to do to find the constant of integration of your velocity?
Plug in t equals 0.
Stick in that guy, plug in t equals 0, and then 25 for v of 0. And then once you find that, what are you going to have to do?
Take the antiderivative of that.
Take the antiderivative again. And then plug in 2 and plug in 100 for s of 2 and find that constant of integration. Okay, good luck. And this is going to be it. So on tonight's homework, yeah, we're not going to get to increasing and decreasing. It's not that big a deal. We'll do that tomorrow. So don't do 1 through 13 off. Just do 15 through 18. That's it. Did you guys, how many people got v of t equaling negative 10t plus 25? Okay, yay. Then let's go ahead and keep going. So s of t is going to be equal to negative 5t squared plus 25t plus c. And then what I tell you, s of 2 is 100. So what do I get? Negative 20 plus 50 is 30, subtract 30, 70.
Yeah.
Did anyone get 70 for that second constant integration? Okay, yeah. And so now I've got an expression, s of t equals negative 5t squared plus 25t plus 70. Yay. Huh? How many people got that stupid answer?
Why do you call it stupid?
I don't know, I just call everything stupid. You have a natural disdain for all things. I'm a misanthrope. Okay, so any questions or problems on this? So hey, you guys, we learned 2 things today. The mean value theorem, that the slope of the secant is equal to the slope of the tangent somewhere within that closed interval, as long as the function is differentiable. And then we learned antiderivatives, which just like derivatives, only evil instead of good. That's it. Any questions, issues? Okay, bye-bye, video.